should respect. So they should be algorithms of right D modules and left KX modules. Yeah, but this is only for a curve. If you do descriptions with higher dimensions would be more difficult. So I have some ideas how to generalize.
これ側にコンストレントが侵略するフォーダーオブジェクト管理。これが、いや、これ侵略フォーダー、いや、違う違う。
Yes, yes. Oh, yeah, yeah, yeah. So I should, yeah. Also, there will be a restriction here, so this should be supported. Yeah, I don't know. So this is KX module, and this should be supported. Yeah, I don't know. Yeah, but this English for
Vertical is that, for example, here, I can use this, that's the
yes, yeah, we have
single part is for corner single.
yes, yes, yes. I think so. Yeah, I do.
You have no single.
Yes, I think you're right. Yeah, we also yeah. Yeah, also at some point I sort of formulating it in terms of but I think the subscription is
This category may be obtained at some sort of module to get some sort of extra.
This is what I think he referred to. He didn't say that we respected, but I think he referred. Yes, I just told them about the gravity. Yeah, so like I have a proof, but we didn't discuss the details. So maybe he wasn't sure enough because they that's the thing. But that's what he meant. Like the modules was additional.
It was in that it seems to be functioning with the coherent shape. Functioning here. There is a function here.
Yes, yes. And so then description was also easy to see what this category has global dimension now. Because everything that zero dimensional support is in SQL and
This is being recognition one.
no. It's actually this category has global dimension.
That should not be X.
It is hereditary. What do
This is here with six to the holonomic holonomic.
this is not holonomic image. It's product security. Yes, it's a workers. For in hard dimension for fine x, it would be equal to the dimension of x. That's for on a fine it would be, but for curves it's one small. X should be usually.
Yeah, thank you very much.
Excuse me. Could you give 2 pages, please?
2 pages?
Yeah.
No.
Oh, maybe if you can 3, that will be good. Well, maybe it's better one by one.
Okay, let me present the next is Dogancan.
Oh, can't mind. Sorry.
Categories. Yeah. It's about problems. Cannot make sense. Yeah, it's really it is not the detail. Be short. Certain here I'll come back to this page. Right now you can just ignore and listen to me. It is when you give a keyword and decorated keyword, it means for each vertex you give some manifold. So you decorate your keyword manifold. You can define it's a length manifold only. With that keyword. And there's some symplectic invariance categories. Symplectic manifold, which is one is a fair category, and the other is the complex fair category, which is this. And our result is we describe them by some PG algebra. This one is PG algebra. There are multiple project algebra, which is in a case is already known. Actually, before this. In these cases, and
It was not.
Yes, I decorate my quiver with two-dimensional manifold. If I do that case is small for generality before us, right?
Morphism presented by some maps. Arrows in the key are they presented by some maps?
Quivers are just arrows.
The vertices.
It actually decorate with that with positive and negative. Plus and minus arrows. But I will say. And also we are describing that as a micro sheet. So we are relating graphical category and micro sheet. But this is in this case it's already known. Right? This is graphical category and micro sheet category. So micro sheet category is already related. This is not here. So this is not our result. But this is something that the component category can also simplify. Describe micro sheet category. Yes.
Yeah, when you say that your rectified category is equivalent to a derived category, do you mean that your so a infinity category is equivalent to a strict category? Is it a derived?
Yes. Quasi-isomorphic category.
So
In a certain way, which I will.
quasi
Girls.
equivalent.
This quasi equivalent, yes, what are quasi? So basically, this is about just talking about three categories, which is one is some modules over some quiver or algebra, other is micro-sheet category, and the other one is a graphical category and relation between them in the context of plumbing. So let me explain this keywords first. The next one. Preliminary. Approach. General picture. Three. Plumbings. 4. Result 1. 5. Result 2. So let's see how far I can go. So that's so first I want to tell you about some conversions here. First, the categories are anything or digit category. As you said, like I work in this setting over some field. But actually you can take commutative ring. I take field for simplicity for stop. So this is first. Second, ignore science. Yeah, I will mess up about science, so ignore that. But the science are very important. And for this talk, I will ignore that. And third, I will use this following correspondence. So if I have keywords, usual keyword. And let's say it's a finite keyword. And let's make it greater keyword now. It's greater keyword. Usually arrows are it's good. With differential. Which means each arrow has a differential. Here I give you an example. From this, you can take half category and get GG category from this one. Actually, it's called semi-free digit series. Which means, because I give everything to you here, this DG category, differential graded algebra. Differentials are here, graded is here, algebra composition is free composition, free to compose errors. So you get DG category. Or you can take algebra and get the algebra. I can also think this as an algebra, just look at the arrows and just If they compose, they compose freely. If they don't compose as an arrow, then their composition is zero. It's DJ algebra. All these notions are equivalent to each other. DJ algebra or finance. So I will move between them actually. So for me, all of them are equal. But sometimes I will say one. So now this Q will be confusing, but English is secure.
The clear has no relations, right? So algebras are very special.
It's with relation. But with differential relation. So it's like nice. Things are not strict, things are relaxed. Because the relation are differential relation. Maybe this example should explain. So let's take this quiver. This is decorated quiver. Same. That's
So it's invisible.
sorry.
What did you put?
What did I do here?
I mean, invisible
I see.
gradient. Too small.
Let's take this quiver. Two vertices. We have two vertices. One loop here, one arrow like this. Two vertices, two arrows. One is loop, one is this. Decoration means I give a orientable connected manifold here. This is S3. Here also I give S3. It's spheres are nice. And nicer than others. Unless you different arrows for plus or minus. What's
You said it's integer. Gradient is integer.
Yeah, actually this is not that. So let's name this That's some other quiver, this is some other quiver. There are different quivers. This is decorated quiver. From this decorated quiver, I can get another quiver of that type. From this, I get A, which is called input DG algebra. DG category or quiver, whatever of this three you want to use. And get this, which defines as follows. It has again two vertices. For each arrow, you double. So X1, Y1. Let's name that. This arrow, you also double that. In arrow, you put the opposite. Let's call this X2, Y2. For each vertex, you put a loop. It's called this H3. It's vertex for V and the rest. This H double. So then to extra loops. You don't need loops in classical definition. For this, I don't want strict relation, so and I need to give them degrees and differentials. I'm trying to get this kind of quiver now. So I have this arrow. X1 and X2 are 0. The original arrows are degree 0. The added arrows, Y1 and Y2, are degree 2 minus 10. And DHV so now this time to ignore signs. Which signs are dictated by this also? Signs in my this differential actually dictated by this plus y. Since I ignore signs, I ignore that discussion. Is this this loop here, x1, y1. There's one loop, you can go for x2, y2, you can get here back. And you can get here, can return here by going y2 and x2. Or the HW. So you're just looking for compatible y-x and xy couples which can fit here logically. So here, only thing I can put is y1, x1. I'm reading from right to left, so y1, x. So from this, you can create a DG category, right? You can take the path category of this, which is composite design. Differential is defined by lightness rule, if you want a differential position. These are my DG category around or Creamer. So next is clear. How I get from usual detector clear on this. Maybe it's not clear because there is S3 here. S3 means you don't do anything. If it's not S3, you do something. So if you say S3 is actually not decorated, you can ignore. Maybe in this talk I won't be able to talk too much about those stuff, but I will mention. Okay. The tree here, tree contributes. Maybe I should make it more clear. It's any string. So let's make it S.
So you define G3. We are defining G3.
Yeah, I defined G3, but now I changed my plan. Okay, let's just anyhow, this is GN. Okay, let me quickly complete this notation here. Business mode. Few. Yeah. What? Using what's A? What A? That time. You take if more means DG category. Whereas objects are this representation of physical pyramids. This DG category of chain complexity of irregular. Your keyword with chain complexes basically up to quasi isomorph. What is this? What means that if my quiver is nice, normally you need to take anything factors. This kind of quivers, we have this definition. If you take this in the more okay. So this means the following. It's a A module. So this A module category is project A module. One way to think about a different way of thinking about this is this. This is the split generator file. It's a different way of thinking about this category. So you don't need to think about modules. You can just look at your keyword. But first of all, this is the strong category, full category of this. So the interpretation of this category which is, we look at this A, we look at this. For example, in this case, this is my A. And let's say I take this perfect produce over this. It means I consider these two things as an object. And these are relation between those objects, the morphism between those objects. And we take this as my generators and generate a category.
It's like projective like projective model. I mean, there are simple modules assigned to the vertex, but this problem.
But it's more general than that. I would say projective model.
Yeah, I mean, because I mean,
You think like system flexible axis that takes split closure. Like this. Pro is bound A modules. That means this is one. Sorry. You represent a bounded chain codes. So it's the three category.
it doesn't mean it's,
I'm sorry.
I mean, by bounded.
Bounded chain complex. So it's degree wise bounded, and also it's a vector space.
Actually, is
Okay, the field that is like that.
finite dimensional complex of vector spaces. That's what.
Yeah, finite dimensional. In the finite dimensional complex of vector space, I think. If it's not vector space, I have to define different. I define it like a perfect complex, actually, definition of perfect complex.
Perfect means usually in cosmology are finite dimensional. Bounded.
You can also take this, but they are equivalent. You can take cohomology level definition, you can take this level of definition. You can take strict definition, you can take the relaxed definition. At least in case field. Doesn't be a problem. If you think about this, in when case field, you can even drop chain complex and make it great modules, great vector space. It's not quite isomorphs. Okay. Let me speed up because I'm slow. So it's some algebraic. Maybe it will be more clear on the example. Let's keep it like this. So let's take a Weinstein manifold. W is Weinstein manifold. That is some exact simplex manifold. With 9 Leo vector field.
It's an extra data. Extra data.
The Leo vector field is not extra data. So Weinstein manifold is an exact symplectic manifold in place. Your symplectic manifold and this exact form. And then Leo vector field satisfies this equation. And not degeneracy of W is unique with Leo vector field. And it's being nice means it's complete and gradient, almost like gradient of some more sport function. So it has, it behaves nice near singularities. or zeros of x. It behaves like gradient. And then a possible skeleton.
Is it correct that this Weinstein manifold is never compact?
Which manifold is always non-compact. It's not compact.
Should be some good behavior of this vector field around infinity, right?
Yes, that's kind of satisfy being nice. So yeah, if you think about this Leo vector field escapes to infinity. See that?
Say singularity.
Singularities are I said singularity. Infinity. So the Leo vector field escapes to infinity, nothing there. Singularity is concentrated in the compact path. Skeleton of. Managed to miracle W. It means kind of retract of W via its Leo vector. So I give you an example, which is potential one. This is a one-dimensional that n is closed. And this skeleton is a zero section. Because we will like the fit escapes to infinity and retract zero section. And if you want other examples of large manifolds, we can think smooth F1 varieties, smooth F1 varieties, or generally Stein manifolds. I think Stein manifolds. From Stein structure, get Weinstein structure. And sometimes I consider this boundary. Sometimes I am a boundary. Which is called Weinstein sector.
What is skeleton in the second example?
Case by case. And
No general.
our chance is certain, depending on which exactly. You just get the singular. And this is only smooth vertical tangent. That's only smooth. The singularity tells you about split formation. You should think like that. Okay. So now, real category. So real category. So first I take this idempotent complete retriangulated problem. So I will show you a category and we take it retriangulated closure. And on top of that, let's closure. So in short, I maybe just objective. Objects are exact Lagrangians. Cylindrical and infinite. It's some plus brain structure, but I will ignore that. Cylindrical activity means it is invariant under Leo vector near infinity. So I have the exact Lagrangians which behaves nice near infinity. So some it's like boring near infinity.
You reach the mean The minimality of the size of your letters, not yet.
Size small.
Yes, it's good.
Maybe this. It says. My Lagrangians are invariant under the Liouville vector field near infinity. So after a compact set, outside that, you can just it's invariant under the flow of the Liouville vector. That's basically the infinity. So those are my objective models are. You see, I have two Lagrange and one Lagrange. The models are graded K module, K vector space. Generated by intersections. So morphisms are given by the intersection of these two Lagrangian, other perturbing first Lagrangian with a Hamiltonian, which is quadratic at infinity.
Whatever h with this condition.
What's the h?
Is it allowed to take whatever h there?
Whatever h, what is quadratic at infinity. Which means it should be at infinity of the form r square, which is r is the cylindrical direction. So that kind of condition makes when you perturb your Lagrangian, the non-compact Lagrangian, it makes it like ramp at infinity. So if your Lagrange is like straight line at infinity because of this condition, when you perturb it, it will become like to wrap around some deep orbit. So that's what ramp comes to. But if you talk about issues, right up there. A lot of people do. Retirement. Exactly. It's determined by some bonus curve counting, so which I won't explain. Okay, so
Excuse me. Ph means the limit of flow action in infinity time, or Ph, phi h.
you take first one. This syntactic form makes a function vector field, right? If you think about it, you can take dh.
The question is it time one or infinity, right?
Right. Yeah.
Is it time one?
It's time one. That's like infinity and infinity. You just focus on one, it's less. So it's like cylinder. Time one here, because of this condition, looks like time. Time one here looks like time, and here. So when you go to infinity, so if you just focus on the part of this, it's like a. If you just focus here, time one, close of here, Like this is like this, right? But here, time 1, time 5 flow here becomes time 1 flow here. But it keeps wrapping and wrapping, that's why. Very good. Anyway, in global it's the ML flow. So tell us the generation result of this rough category. So generation result. The formula Chandler. And that's the right side, maybe first. Sorry. Campaign Dimitro result. PG holograms.
But this letter is even smaller than first.
Okay, I will make this. Another partner Chandler, they and this generation result says. It says the following. For that 5 also and dimensional for dimensional machine for generate paper. So you don't need to understand Lagrangians in a rough category. These particular Lagrangians actually generate everything. So if you understand the cotangent fibers, sorry, what is that? I will tell. So let's see what I mean by this cotangent fiber. Oh, I sorry. Skeleton W. Skeleton of W. Okay, let's look at this example. This is this is a marginal manifold with boundary. There's a boundary and this is infinity part.
2 dimension.
2 dimension. This is 2 dimensional. And then we draw real vector field. It's set to infinity, right? Okay. So it escapes to infinity. It's real vector field. And if you retract,
Even smaller.
or if you retract your simplex manifold via x, the reverse x, we end up depends what actually how we may end up like something like this. This is your skeleton.
So I can see the lane picture. Or is it?
This is really like as you say, this is really is not behind them. This is boundary. This is just this should not this build supposed to do. The skeleton is this thing, which is 3 long vertex. And what are these cotangent fibers, which are actually called cocords. Lagrangian cocords. Like I could say Lagrangian. This called Lagrangian cocords, and we take cotangent one. It looks like this looks like cotangent. So you take it like numbers, cotangent fibers, sorry. Yeah. Wow. That's the cotangent fiber here. Yes, let's call it L2 and So there are three Lagranges generate this graph characteristics. If I understand how they relate to each other, and then I'm good. So if you, so how do they intersect? So if I want to face some, so the graph category of this thing, I want to understand this. Graph category of this thing is generated by these three Lagranges. Remember my notation, mod per. If I use this notation, it means I want to forward this, I count my generators. So L1, L2, and L3. And three generators. And then I need to tell how they intersect each other. Here, it may seem like they don't intersect, but when you read L1 intersect with L2, because graphing is kind of this direction.
Once or many?
That's it.
Once or many?
Once because there's no reorbit here. Like this reorbit. If it were like loop, that will be implemented. So kind of rip flow is this direction. Counterclockwise, let's say, assuming this kind of split form. L1 after wrapping will intersect with L2, but L2 won't intersect with L1. So you can think like L1 is intersecting like this. You can take L2 is also intersecting like this. And L3 intersecting L1 like that. So there is a morphism. Each intersection is a morphism, right? There's a morphism from L1 to L2. So the morphism from L2 to L3. There's a morphism from L3 to L1. But there's no morphism. If I look at this, if this intersects with this way. So only if I have this morphism. And plus I need to count holomorphic disk, etc. But one particle holomorphic disk starts with that. Look at this tree. They bound a disk. Only this kind of disk here. Here I just it means this is an exact triangle. Exact triangle.
And degrees? 0?
And degrees. Because it actually shift L1, L2, so it's kind of free, but you can say
For this particular one.
F and G0. H is 1. And you compose all of them.
This particular.
This particle. No. Because I choose particle L1. There's a shift of L1s also.
You can just take this one, right? Without shift.
Without shift. There's no without shift canonical. There's no without shift canonical. There's no canonical picture here.
Actually, pair of 1 and 3.
You need to break cement here. There's no canonical picture. So since this exact thing, what's the exact triangle? Other than L2, generate L3. So actually I can ignore L3 also. And I can write this. You just generate squares. L1 and L2. And a single error happens.
And differential is 3.
Actually, here is differential, so I should, instead of differential, I should put G equal to H G equals 0.
But GF is 0, right?
Here, H all time 0. Or you can give a semi-free model, but I won't do that. Then you add more and more. Okay, this picture is just representation of this is just A2 quiver. A2 quiver explains this picture. So this is a quiver what can be the correspondence, this kind of thing I'm aiming. Actually, this kind of thing, actually, this story is similar in the first result. I'm trying
Something of American Kansevich Katsarkov. They had this kind of description for surfaces.
and so many descriptions, so many examples. Not just for example.
So you mean that the number of the homological polygon is just one?
In this picture,
Yes.
and here is just this is actually contributing to mu3. Mu3 of this is equals to 1. So that means actually that's definition of, in a way, exact term in infinite setting.
But do you have examples that not equals to one?
Yes.
And
Yeah. The number of moments to this given, right?
yes.
Yeah. Even take step one and proper of some
Sorry, what is W?
sensor. S1 and S1. If you perturb S1 and S1, then there will be two homomorphic, but they have opposite sign. Actually, they will cancel each other. Yeah, since I'm fine. And 60 minutes left, even though I'm not explaining what I want, I will let me reconstruction my talk. And let's continue. Okay, so I will mention this story of farming. I want to give you this picture with the microchip side. Well, so before this, I forgot to mention. Okay, I defined rough category, but I didn't define compact category. Let me define that. Compact category. Just I wrote category. Same definition, just ask this to be compact. That's the compact category. So if you think about it, then you won't have any wrapping thing because compact Lagranges are in compact region. There's no wrapping. This story is not necessary for that. This wrapping thing. Yes.
Is this Lorentz zero? Example. Is this Lorentz zero in that?
Okay, that example is a bad example. Because there's a boundary. I don't consider this definition when there's a boundary. But there's an one other than category there which is not zero, but I want to talk about this. Yes. And simple version just take me. So what the shape category is, I define on the skeleton. And I define in a shortcut way. Actually, I won't even define it. Just say it is it's a DG category. Objects. So objects are locally constant. To say derived locally constant shifts. Locally constant shifts on the union of n-dimensional squares. Plus some restriction maps and conditions. Maybe try to say that. But some that. Conclusion. Yeah. Choose to define this.
So, friction maps from where to where?
And that also will be apparent in the example. Because I cannot define actual definition. It's impossible. Present. Given time. And that. But let's talk about that example. And I want to describe microchip on that skeleton, blue thing. So previous example, skeleton was this. So to my code, one-dimensional skeleton and top dimensional strata, which I erase this singular point and give a locally constant sheet on this, which is constant sheet here, constant sheet here, constant sheet here, three constant sheet here. Remember, so it's described by its stock in a way. This constant sheet is described by its stock. But this is a sheet of digit chain complexes. So each stock is a chain complex. And chain is vector space. But this when around this, if you look at this around this, and also there is three sections. Now it's like basically I'm not describing you microchip, but microchip theory says that if you have this kind of meeting at singular point, which is trivial and vertex meeting, it says that there's a restriction from this to this, restriction from that, I mean here, this to this, this to this, and this to this. This kind of restriction map that single point induces. With the local picture, if you have more complicated graph with trivial vertex, same idea applies. You can just write this idea there. And such that is exact triangle. This is exact triangle. If it's envelope vertex, then there will be also this cycle behavior. Restriction from first one to second, second to third, third to fourth to five, and back. And iterated cone of first n minus one will be the nth one. So if the cone of this two is this one, if I have more, I will have bigger cycle, and cone of this with cone of that with cone of that will be the last one, kind of relation. This is the microchip theory in the dimension one, in nutshell. So microchip category. This case is a category where objects are of the form and chain map. So these are chain maps, restrictions are chain maps. Where the last one is the degree one chain map. It's not chain map. Objects are, you can just take it as a this part because C is automatically determined. That stock is automatically determined. So objects are of this value. A and B chain concept. And chain length. Morphisms are just morphisms of sheaves. But if you think about it, this is representation, so be clear. Remember, what is representation of the group? So this category is representation. So out of this, we define two other categories. Once we have microchip category, there are two other categories, which is microchips. And the other one is bounded microchip. And then define, if you, shortcut is, if you define this microchip category as a modulus over some quiver, that microchip is defined by perfect modulus over quiver. And bounded microchip is defined as and proper modulus over that. And if you can realize, this is actually flexibility.
Finite dimension.
Finite dimensional model, which means I ask A and B to be finite dimensional. So bounded chain complexes with made of bounded vector spaces. Okay. So let me tell the big picture and say the definition of Lambda space. And I'm going to here. So we have this following categories given by minute. So we have one category. That's right. And then full subcategory of this, which compounds category. And just made of compound operating centers. So then there's this microchip category here. Then we have the direct version. And then bounded version. They also conference. There is this motion over some keywords. Perfect motion over that keyword. Something motion over it. So idea is, so this is a theorem now. This is another convention. GPS. To this, and getting finite keyword is selection of results of that convention and not that. Me and my collaborators. Sergeant Lee. And if you can get this some keyword, getting nice finite keyword is not guaranteed normal, but we show in my case, you can always get a nice semi-free digit category here. That's all digit algebra of finite. So this direction is what many things wrong about compound? This one, no, this is not. These are automatic. Once you have this, let's say you run the keyword, I have this and I have that. So I can describe my option category via this, some keyword, horizontal keyword. That there's a compact Fukaya category. Can we describe problem modules over here or micro shapes category? That's not known. It's only known of a few cases, which is not as a last code. Yes. If it's cotangent bundle, then this is not. Other than that, we don't know. It.
So you have an inclusion from the right hand side to so left hand side to right hand side.
That's right. That's yeah, clear inclusion. So we prove this part for this plumbing space. Basically, this is result 2. We prove this compact category can describe micro shape. And we also describe this Q, because Q accessed by which Q? We describe as a Ginsburg DG algebra. And what is plumbing? Construction is really simple. 2 minutes. It is something associated with decorated quiver. Let's then go back to this decorated quiver, this sentiment. Q. Remember, what was my decorated quiver? So this loop, appear this arrow. Plus, right? And this was S3, this was S3. So from this, I can create a topological picture, if you like. This first is S3. So it says I have 2 S3 sphere. For simplicity, just take, let's make it S2 and T2. S2 and T2. Sphere and torus. I say it's sphere. And I have torus. So this arrow says that S2 intersecting T2 one time, one arrow, and positively. So they intersect positively. Transversely.
Are you drawing the skeleton?
Yeah, I'm drawing actually skeleton. Actually, you can do this in this asymplectic manifold. Take a symplectic manifold. Take some Lagrangian in that symplectic. Any symplectic manifold doesn't need to be an exact. Take a symplectic manifold. Take a Lagrangian in that symplectic manifold. Some collection of Lagrangians. And take the union. Those Lagrangians. But assume they are transversely intersecting. You should take the union. And look at this neighborhood. There's a theorem, Weinstein neighborhood theorem generalized. The Weinstein neighborhood theorem says if you take a one Lagrangian, this neighborhood always looks like T star L. There's a generalization to this setting when if you're transversely intersecting Lagrangian, and if you look at the neighborhood of it, it's a standard. It doesn't depend on ambient space. And it is called plumbing. And I'm describing skeleton of such a thing. So this is in a symplectic manifold. I have 2 Lagrangian and 2. This is like intersection diagram of this is how S2 and T2 intersect in a symplectic manifold. So S2 intersect with T2 positively at one point, and S2 self-intersect. This means self-intersect. Look, it's self-intersect. And this is the picture. This is the skeleton plumbing. And you kind of take a potential bundle of this. Some neighborhood of this. This is my this skeleton, this neighborhood of this in the whatever setting you take this is a plumbing space. And if you just take Q over with 1 point, it is just cotangent bundle. But this is like this is just generalization of cotangent bundles where there are many cotangent bundles intersect with each other. And we are saying this: if you start with that quiver, decorate quiver, create this picture and create this Weinstein manifold, then we describe this draft Fukaya category and compact Fukaya category via that quiver. And would be algebra over that quiver. Not that, yeah, that quiver in this.
How you define differential?
Differential, actually, I describe,
Formally.
I describe how to create differential, right? So you have loop and loop has differential and nothing else has differential. Just maybe the question could be, this space is me, but maybe I should not say more. Let's do it. I guess.
Questions, please.
To define Rafter category or category. To define Rafter category or category of microsheaves, actually you have to choose master of data. So in this case, master of data.
Yes, good point. Actually, this story, I like to catch it. So this story is not complete without giving an extra data to Rafter category. So to give a grading, so what is a fit category? You have grading, so this intersection point, right? But that grading you cannot give canonically. You need extra choice on W, which is essentially corresponding to even if you're selecting a fault, it's each one of that many choices, which have, and there's no canonical choice, which affects the gradings of the Lagrange intersections. Actually, in our paper, we consider those things also.
So how does the choice affects?
So if you this one comes to this example,
It's about mass of effects, right?
choices. Choice is actually you choose a trivialization of bicanonical bundle of this W. And that choice change the mass of indexes. So let me quickly say, if this is Q, if this is Q, the corresponding gives the algebra. Like this dimension for this lattice. Let's ignore that. Make S two. SM. Let's make this SM. Corresponding gives me the algebra is this quiver's. I double arrows, remember. I has one loop. Double note, right? And as you remember, this one, x1, x2, y1, y2. And there's some differential relation. That didn't change, but I said you show x1 is degree 0. X1 is degree 0. Y1 and y2. So minus m. I said this. So grading changes this. This becomes free. This becomes x1 becomes, let's say d1. X2 becomes d2. Y1 becomes minus n minus 1. Y2 becomes. So the example I show is just one particular grading structure where this both is 0. And sometimes choosing D doesn't affect, it's up to something, it doesn't matter what you put here. It doesn't change category, but for example, for this loop, it changes. The degree of X, what is this? Sorry, this is Y1. Degree of X2 matters. If you change it, category changes.
Okay, thank you. We can continue discussion on the third floor. So let's thank the speaker again. And we resume at 4 o'clock.